So last time we were wrapping up this example on Moore's circle, right, demonstrating that. And we found the weld angle, right, theta, which was, we redefined it, right? So we redefined this weld angle as alpha based on this orientation where theta represents the angle of that stress element, or the right face of that stress element, so that the stress in the weld, the normal stress in the weld, is not greater than 5,000 psi. So we came up with an alpha of 60 degrees, and that corresponds to a stress element rotation of 30 degrees. Based on the figure, that's going to be a counterclockwise rotation. And then the last thing I was doing was showing you the stress states, and I was a little rushed for time, and I got lost in the tall grass myself looking at this, and I said, oh, these are not correct, they're inconsistent. Well, and then I looked at them again after class, and I realized actually they are correct. So I'll talk through them here, and I'm actually going to redraw the lower one because it looks a little sloppy right now. So here we have, right, just one correct way to draw the stress state would be to orient it as it was given to you, in this case aligned with the x, and then rotate that x-axis by theta, right, in the appropriate direction. Draw that new axis orientation, and then sketch your element oriented perpendicular with the right face perpendicular to that axis. And then draw the stresses on that face, right? So this original x face would translate to what you found when you moved 2 theta on that Moore's circle, right? And in this case, that was going from this point to this point. So then the shear stress, since it's in the lower portion of the Moore's circle, that corresponds to a positive shear stress in the physical space. So that tells us which direction to draw the shear stress arrows, right? In the positive x direction on the positive face. And then, as you recall from previous classes, right, the shear stress on the other faces will be oriented so that the arrows meet up at the corners and the tails meet up at the opposite corners. It's always important to make sure that you include units somewhere on your sketch, right? You can do something like this, like everything's in KSI. And then a slightly less involved and simpler way to sketch all this information would be to just show the rotated stress element. So again, I'm going to just re-sketch that here. So rotate it. And then include a vertical line that represents the original position of that reference face. Make sure that you show the angle. And then include the stresses on that face. So you don't have to draw the normal stresses on all 4 faces, just on one representing the x and one representing the y. So this one would be your sigma y of 7, sigma x of 5, and then the shear stress. All right, just being consistent with the positive shear stress direction, which on these 2 faces would be shown with the arrow trending downward. All right. So that's got everything that you need for a complete stress state sketch. All good?
those ones above the x's and y's, or those primes?
It's a prime, yeah. So what we're showing are these. Oh, I guess up here I did ones, didn't I? Yeah. Okay. Fair enough. So I think either.
No, it's the same thing, just different nomenclature.
Yeah. Same idea. Yeah. Yeah. I'm trying to remember if it was noted. I guess in the equations I use ones, so I'll be consistent with that. And then, but with the axis, you typically use primes, so that's what threw me off, and I can understand. Yeah. Fair question. Oops, what did I do here? Don't want that. All right. Good deal? Okay. Very good. So on the next couple pages, there are some more examples of Moore's circle application. In these examples, I just want to point out that instead of how I, in the notes, noted the center of the circle as C, these examples use D to represent the center of the circle. So just a quick distinction there. And then on the second example is demonstrating an application of strain with Moore's circle. So that's here for your reference. And then that leads us to the next topic, which is Hooke's law. And most of this should also be review for you guys. You've all seen Hooke's law before in mechanics of materials. But before we dive into that, do you have any questions on Moore's circle or any of the stuff that we just talked about? Okay. All right. So, as you know, stress and strain are related to each other by material properties, and we call those relationships constitutive equations because it relates to the constitution of the material. So we have, your material properties specifically are Young's modulus, Poisson's ratio, and the shear modulus, which is capital G. So all of that should sound familiar. And you have probably been exposed to the definitions, at least, of these two types of materials, isotropic and orthotropic. Does that ring a bell? Yes, okay. All right. Huh?
I remember what they mean.
Fair enough. That's all right. That's what this class is for. We're going to pick up with that and move forward. So in mechanics of materials, you mainly dealt with isotropic materials, probably exclusively dealt with isotropic materials. In this class, we'll look at isotropic materials again, but we'll also show you how to deal with orthotropic materials. So but we won't do orthotropic until Friday. So today we'll just define the terms and then focus on isotropic. So an isotropic material is one that has the same material properties in all directions. Examples of isotropic materials include glass and metal. Orthotropic refers to a material that has different properties along three mutually orthogonal axes. So an example of orthotropic material is wood. Did any of the structure students take wood design class? Yeah, okay, so you're familiar with that concept. Different material properties along different axes. All right, so once again, we'll come back to orthotropic materials on Friday, but today we'll focus on isotropic. So generally speaking, for a cube of unit dimensions, or the unit cube, if we apply a normal stress in just the x direction, and if we assume that the material here is isotropic and elastic, I'll say if sigma x then the strains in X, Y, and Z can be computed by the following equations. Normal strain in X is 1 over Young's modulus times sigma X, and normal strain in Y is equal to normal strain in Z, and both of those are equal to negative Poisson's ratio, which is that Greek letter nu, times sigma x over Young's modulus. All right, and if you recall, the formula for Poisson's ratio is it's the ratio of the lateral strain over the longitudinal strain, but negative. All right, so that should all look familiar. Now, if we remove that normal stress in X and separately apply a normal stress in Y, then we have our normal strain in X and Z both equal to negative Poisson's ratio times sigma y over E. And normal strain in Y is equal to 1 over Young's modulus times sigma y. And then similarly, if we remove that sigma y and apply sigma z, sigma y removed, and sigma z applied. Then we have normal strain in X and Y, both equal to negative Poisson's ratio times sigma z over Young's modulus, and sigma z is, or normal strain in Z is 1 over Young's modulus times sigma z. All right, nothing new or groundbreaking there, but important enough to note in this class still. On the next page, we've got the equations already written out. You're welcome. If all three stresses are applied at the same time, right? So we have these equations written in two forms, right? First in terms of strain, and then in terms of stress. And these are what we call those constitutive equations. Now on the next page, you'll see a handout that includes the equations for stress in the condition of plane stress. Or I guess the equations of all these, right, for the condition of plane stress. And that simplifies them quite a bit. So they're on the next page for your reference if you're dealing with a plane stress situation. Now, this last term down here, lowercase e, being the sum of the normal strains, is used to represent the dilation, or approximately the dilation. So that is specifically, there is a symbol for that. We use K, and it represents the volume change per unit volume. All right, so we can write it as change in volume divided by volume. And for very small strains, we can say that this sum of the normal strains is approximately equal to the dilation. All right, and then last but not least, we have our shear constitutive equations. So those are always simpler. You just have gamma xy is equal to tau xy over the shear modulus, and so on for yz and xz. And as a reminder, that shear modulus is related to the other two material properties, right? So these three material properties are not all three independent, right? Only two of them are independent. So if you know two of them, you can calculate the third. And that relationship is, that is not what I meant to do. That relationship is expressed by this equation. All right, questions so far? All right, so again, next couple pages have a handout which summarizes these constitutive equations for certain cases. So start off with the simplest, right? Uniaxial loading, planar shear loading. And then here is that plane stress condition where you have the strains and the stresses written out, slightly simplified from the previous page. Then go on to plane strain, pressurized thin-walled cylindrical tank. So if you've got a situation like that, you can go straight to these equations to calculate the stresses here. All right, and then on to the next page, got 3D solid and then in matrix format. All right, so sometimes it makes sense to use matrices to solve these problems. Other times it overcomplicates things. So just think about what you have in hand and whether it makes sense or not to use these matrices to solve it. All All right, so now we're gonna talk about strain energy. So this concept is something that we'll come back to later on in the class. I think probably not until end of September or October at the earliest. But we're gonna introduce it here and in the context of Hooke's law. So first, we're going to define strain energy density. That is specifically energy that is stored in a unit volume of a material that is under some kind of load. So if we consider a unit cube that is inside this axially loaded elastic rod, all right, so we have some axial load applied here. If we plot the stress strain curve, right, in the elastic range, it's linear. All right, and the volume under that curve represents the strain energy density from the unit cube. So, all right, that axial force would generate a normal stress in the x direction on that cube, right? So that's what we're plotting here. I'll just make that clear. All right, so we can refer to that as a lowercase u with an underscore to represent the strain energy density. And to calculate it, it's simply 1/2 times the normal strain in x times the normal stress in x. All right, so that's the area under that curve. Sorry about that. For the strain energy in the entire axial rod, right, so the whole volume, assuming it's under a uniform stress, we would integrate the strain energy density over the volume. So we could call that a capital U for the strain energy in the whole volume. And then we got a triple integral of lowercase u with an underscore over dx, dy, and dz. Or to simplify that expression, right, we can write it like this. So if we simplify this consideration to a plate that's under plane stress, then normal stresses in x and y would generate normal strains in x and y. And the strain energy density in this scenario would be equal to 1/2 normal strain in x times sigma x plus 1/2 normal strain in y times sigma y. So it's simply, right, separating the normal stress strain curves, right, and then summing the volume or the areas underneath those curves. Now, if there's also shear stress at play that contributes to shear strain, then the total strain energy density would simply add a term for that shear stress. Now, if we apply the constitutive equations to substitute our stresses for strains, we can obtain this expression below for the strain energy density in terms of stresses and only stresses. And this equation is specifically for plane stress. So I'm going to go ahead and make that distinction on this page, right? This lower chunk focuses on plane stress, where the stuff above is related to the more general introduction using just the uniaxial loaded rod. So now we'll go to an example that applies Hooke's law. So here we have two stress states provided that are considered separately from separate applications on a plate in plane stress. So we have a plane stress condition, and we're asked to determine the resultant strains in normal in X and Y, and then shear strain from each applied stress state. We're given the material properties, or two of them at least, and the X and Y directions are given in the traditional horizontal vertical sense. All right, so we'll start with the first stress state, A. And we'll start by using Moore's circle. So if we look at this stress state, what do we know about it right off the bat? Yeah.
It's in the principal stress?
Exactly, yeah, it's in the principal plane. So we can say that it's a principal state. I'll say and so our reference point, if we're using the right face, all right, from our X, Y orientation is just this guy right here. So our reference point would be negative 300 and 0. All right. And then the center is always going to be the average of the two normal stresses. So in this case, negative 300 and positive 250. So that gives us, that locates the center at negative 25. So we can go ahead and plot our reference point here. And since our center is negative 25, our reference point is out here. We can sketch in the vertical axis. It'll be somewhere to the right of the center. Add units to our sketch. And then since we're starting out with the principal state, it makes things a bit easier with regard to drawing Moore's circle, right? So the radius is easier to find. And then we can go ahead and calculate, so what we're interested in ultimately are the strains, right, in X and Y. But first we need to get stresses. So we want the normal stress in X and the normal stress in Y. So to get from this principal state to the XY state, we need to rotate 30 degrees clockwise on Moore's circle. Or 30 degrees clockwise in the physical, right, which is 60 degrees clockwise on Moore's circle. So something like this. So to calculate that, we can find it using circle relationships. So from the center, for sigma x, we have the center minus r cosine 60. All right, so that's just looking at this geometrically. I'm going to go ahead and draw the diameter in. That's close enough. There's our center point. R minus cosine of 60. That would give us negative 162.5. And then for sigma y, we're using this point down here. So that'll just be C plus r cosine 60, which gives us 112.5 megapascals. This is obviously not drawn to scale. And then the shear stress is going to be R sine 60, or 238 megapascals. So really, once you have Moore's circle set up, all you really need is your reference point, the center, and you need to know the radius. And then for any point of interest, you can just use geometry to calculate what you need to know, right? Now, what about the direction of that shear stress? Now we've got the magnitude. Negative. Yep, so negative shear because it's in the upper half of Moore's circle. So translating that in the physical space, right, we would sketch it like this on the right and bottom sides, respectively. All right, so now that we have our stresses, we can go ahead and calculate the strains. All right, so Young's modulus was given as 100 times 10 to the 9th pascals. And Poisson's ratio was given as 0.33. So we can calculate the shear modulus. I'm going to rewrite this as 10 to the 11th to be consistent in, I don't know, just to simplify it there. So 10 to the 11 over 2 times 1 plus 0.33 at 37.6 times 10 to the 9 pascals. And then using our Hooke's law equations, we can calculate the normal stresses in X, or normal strain, excuse me, in X, 1 over Young's modulus times sigma X which is negative 162.5, minus Poisson's ratio times sigma y, which is 112.5. And then those are all megapascals, so you have to multiply that by 10 to the 6 to account for the units, and then that gives us negative 0.00199. And then similarly for normal strain in Y, same equation, we just swap the normal stress values. And that gives us a positive strain of 0.00166. And then for shear strain, we take 1 over g times tau xy. We're plugging in a negative value here because we interpreted, right, our shear is negative from Moore's circle, so negative 238 times 10 to the 6. And that gives us negative 0.0063 radians. I know this is kind of tedious, I apologize. Things will get a little bit more interesting on Friday. Still tedious, but at least a little more interesting. All right, so the next part, part B, gives us the state of pure shear, right? And so that's rotated 20 degrees from the XY. So starting with Moore's circle, right, since we know it's pure shear, we can go ahead and place that vertical axis at the center of Moore's circle. All right, so here's our reference point. And from there, we want to rotate 2 theta in which direction to get to our XY state? Yes, you're correct, counterclockwise. All right, so, and 2 theta is 40 degrees. So something like this. All right, so this point will give us our sigma x. And this point will give us our sigma y. I'm going to not write the tau xy part because that's redundant, or it seems repetitive anyway. We know that we're going to get our tau from those points too, right? All right, so now using geometry to get those values, we can calculate sigma x is going to be just negative 70, right? So we know the radius is 70. We don't really have to do as much as we did in the first part, times sine of 40. So that gives us negative 45 megapascals. Sigma y will be positive 45. And the shear stress will be negative 70 cosine 40, which gives us negative 53.6 megapascals. All right, and then plugging in values for our constitutive equations, we would get normal strain in X of 0.006. I will spare you the repetitive calculations. Normal strain, positive 0.006, and shear strain of negative 0.0014 radians. So in the problem statement, it said that those two states that we were given were applied separately. And so we solved for them separately. But if those states were applied at the same time, or if we wanted to know, what would it be if we combined those, we simply just add the results from the two separate analyses, right? And we can do that because it's assumed to be an elastic material. It wasn't said in the problem statement, but for most of this class, we'll assume elastic behavior. You'll know when you're not dealing with elastic behavior. That's later in the class. So I'll just make that note. All right, questions? All right, so on the next page is an example demonstrating the application to a granite cube, all right, with, and this is a three-dimensional problem, right? So you have normal strains in all three directions, and then you're asked to determine the corresponding principal normal stresses and the maximum shear stress state, as well as a few other things down at the bottom there. So this is a scenario where it probably makes sense to set up the matrix and solve it that way because it's a three-dimensional problem. So if you do that, then you just have these terms, right, that are defined. And these are all defined in the handout from earlier in the lecture, right? So these diagonal terms, right, are all going to be the same in this case, the first three anyway, right? And then the off-diagonal terms in the normal stress, normal strain quadrant are going to also all be the same value in this case. And then you have the values for the C44 element there, right? And in this case, let's see. Yeah, so have that from loading, yeah. All right, and this, I believe this should read, all right, this should be, these three diagonals should all be the same here. I don't know why it's not written out like that. But ultimately, right, you can solve that system and obtain those principal stresses by well, in this case, right, we recognize, so there are no shear strains at play, right? So it is a principal state that's given. That's what I was missing. All right, so your sigma x, sigma y, and sigma z are going to be your principal stresses. And then you can go from there and find the maximum shear stress state. In this case, taking the difference between the two extreme principles, and then change in volume, right, using the dilation formula, and then strain energy density using the formulas provided on the previous page. Total strain energy is taking that density and applying it over the whole volume. So, you know, you don't actually have to do the integrals and the calculus in this example because it's a straightforward geometry, but that was provided for a general application. Right. Questions? Good deal. Well, I'll see you on Friday then.